Hope is not wishful thinking or passive optimism. It is a sophisticated neurobiological system that literally reshapes neural architecture. The brain that hopes is running complex simulations about possible futures, activating reward circuits and building the infrastructure for survival. The prefrontal cortex, the seat of human planning and decision-making, becomes more active when hope is engaged. Neuroimaging research shows that hopeful states activate specific regions involved in goal-directed behavior and emotional regulation. The medial orbitofrontal cortex shows distinct activity patterns in individuals with higher trait hope. What makes this remarkable is the bidirectional relationship. Hope activates these circuits, and strengthening these circuits through deliberate practice increases the capacity for hope itself. Hope and optimism are neurologically different. Optimism is the passive belief that things will work out. Hope requires both the belief that a better future is possible and the perception that pathways exist to achieve it. This dual requirement engages multiple brain networks simultaneously. Researchers call this agency thinking and pathway thinking. The brain is not merely feeling good about tomorrow. It is actively mapping the routes to get there. The neurotransmitter dopamine has been profoundly misunderstood. Popular conception treats it as a pleasure chemical released when rewards arrive. The actual neuroscience reveals something far more interesting. Dopamine fires not when rewards are received, but when they are anticipated. The brain's reward system is fundamentally a prediction machine, constantly calculating probabilities about future outcomes. When dopamine neurons light up, they are betting on tomorrow. Research demonstrates that dopamine neurons encode a probabilistic map of future possibilities. Some neurons specialize in immediate rewards, while others respond more strongly to delayed outcomes. Together, they form a population code guiding behavior through uncertainty. The ventral tegmental area, a small midbrain structure housing critical dopamine neurons, plays a central role in goal-directed behavior. These neurons project to the prefrontal cortex, forming circuits that regulate motivation and the pursuit of rewards. When this system functions well, it creates a positive feedback loop. Anticipating rewards motivates action, action produces learning, and learning refines future predictions. Chronic hopelessness disrupts this system at the chemical level. When the brain learns to predict that rewards will not come, dopamine signaling diminishes. This reduces motivation and prevents actions that might produce positive outcomes. Breaking this cycle requires deliberate reactivation of anticipatory reward circuits. Achievable goals rebuild the brain's confidence in its predictions. The relationship between the prefrontal cortex and the amygdala represents one of the most consequential dialogues in human neurobiology. The amygdala responds rapidly to perceived threats, triggering cascades of stress hormones and defensive behaviors. The prefrontal cortex, evolutionarily newer and slower, evaluates context and weighs options. It can suppress inappropriate fear responses. The balance between these structures determines whether uncertainty produces adaptive vigilance or paralyzing anxiety. Resilient individuals show stronger functional connectivity between prefrontal regions and the amygdala. This allows more effective regulation of emotional responses. Research demonstrates that greater prefrontal activity during emotion control tasks predicts lower development of trauma-related symptoms. The prefrontal cortex literally quiets the amygdala's alarm bells, creating cognitive space to assess threats accurately. This prefrontal amygdala circuit is not fixed at birth. Studies confirm that the connectivity between these regions changes with experience and can be deliberately strengthened through specific practices. Mindfulness training increases gray matter density in prefrontal regions associated with emotional regulation. It simultaneously reduces amygdala reactivity to stress. The brain learns to maintain executive control even under challenging conditions. Even individuals with trauma histories can strengthen these circuits. The brain retains remarkable plasticity throughout life, allowing new patterns of regulation to develop. The architecture of fear can be rebuilt into an architecture of resilience. One of the most counterintuitive findings in resilience research is that exposure to manageable stress actually enhances the ability to handle future challenges. This phenomenon is known as stress inoculation. Stress inoculation operates much like a vaccine. Introducing the system to small doses of a stressor builds immunity against larger exposures. The brain that has successfully navigated moderate challenges develops resources that protect against overwhelming adversity. Research in primates demonstrates this principle dramatically. Monkeys exposed to brief, intermittent separations during early development showed enhanced stress regulation, greater cognitive control, and larger prefrontal cortex volumes. The key variables were timing, magnitude, and controllability. Stress occurring early in development, remaining manageable in intensity, and allowing influence by the individual's behavior produced lasting adaptive benefits. Controlled exposure to challenges activates the stress response system in ways that promote calibration rather than sensitization. The brain learns its own capacity for coping and builds confidence in its ability to regulate arousal. The goal is not eliminating stress, but cultivating appropriate exposure to challenges that stretch capacity without overwhelming it. Each successfully navigated difficulty becomes a deposit in the bank of self-efficacy, funding future resilience. The adult brain remains plastic throughout life. This represents one of the most transformative insights in modern neuroscience. Neural pathways strengthen with use and weaken with neglect. The patterns of thought and emotion that currently dominate can be deliberately reshaped through consistent practice. The brain is not destiny. It is a work in progress. 8 weeks of mindfulness-based training produces measurable changes in brain structure. This includes increased cortical thickness in regions associated with attention and emotional regulation. Long-term meditators show enhanced connectivity in the hippocampus, a structure critical for memory and stress regulation. They also show reduced reactivity in fear circuits. These are not temporary states, but enduring structural changes. Any consistent practice that engages desired neural circuits strengthens those circuits. Deliberate cultivation of gratitude activates reward systems and shifts attentional biases toward positive information. Visualization of future goals engages prefrontal planning networks and reinforces pathways between intention and action. Social connection activates systems that buffer stress responses. Building a resilient brain requires treating neural development as an ongoing project rather than a fixed inheritance. The circuits supporting hope and adaptive coping can be strengthened at any age through intentional engagement. The brain that learns to anticipate positive futures, regulate emotional responses, navigate controlled challenges, and maintain flexible attention is the brain that thrives amid uncertainty. Hope is not found. It is built. As we've seen across these diverse topics, from understanding complex neuroscience to mastering practical skills, the underlying principle remains. Your brain is an incredible tool for growth and adaptation. We've explored how hope itself is built through neural pathways, fueled by anticipation, and strengthened by practices that balance emotional regulation and resilience. Remember, consistent effort in areas like mindfulness can reshape these circuits, fostering a greater capacity for optimism and navigating life's uncertainties with more ease. Thank you for watching. Please leave a like and share your own experiences. What unconventional topics have you found fascinating to learn about?